Good afternoon, everyone. This is Carlos Morillo, and again, welcome to our webinar for this week. Today, we are going to be talking about the circular dichroism. This is our second webinar on this topic, but today is going to be more focused on the sample considerations and parameter optimization. Today, again, we are going to be listening Dr. Leah Pandisia. And for those that don't know her, I just want to let you know that she worked for a medical device company as a chemist for a year before she went back to school and received her PhD from Drexel University. There, she worked in an spectroscopy lab studying biophysical chemistry, and now she is a spectroscopy application scientist at JASCO for circular dichroism, UV visible near IR, and fluorescent spectroscopy. So with this, I led you with Dr. Pandisia. So Leah, go ahead.
Hello, everyone. Good afternoon. I hope you are all doing well today. I just want to quickly apologize for the barrage of emails we had sent last minute. We had an issue with our email list. But thank you for joining us today anyway for part 2 of our Circular Dichroism webinar series. So in case you missed the last presentation, JASCO Corporation, or the Japan Spectroscopic Company, was founded in 1958 by a Nobel laureate spectroscopist. Today, our headquarters and factory are in Hachioji, Japan, with our Americas office located on the eastern shore of Maryland. While the first instrument developed was an IR spectrophotometer, JASCO now offers a wide range of spectroscopy and chromatography instruments, including circular dichroism, where we have been the world leader in research and production since 1961. Today's seminar overview will go over sample considerations, measurement parameter optimization, and a few data processing functions. So if you missed the first CD webinar, to quickly review, circular dichroism is the difference in the absorption of left and right-handed circularly polarized light. CD signals are observed when a chromophore is chiral or optically active, and aside from being intrinsically chiral, you can observe a CD signal when a chromophore is covalently linked to a chiral center or placed in an asymmetric environment. CD is uniquely sensitive to a molecule's asymmetry and provides information on the molecular and electronic structure. The experiments are relatively quick and easy to perform and are non-destructive, so unless you're doing an irreversible denaturation measurement, most samples can be recovered. It's done in solution phase, so the crystallization process could potentially change a molecular structure. So by doing it in solution phase, we avoid this. However, CD measurements can also be done on thin films and solid samples. And it uses low concentration, so roughly 0.1 mg per mil, so it doesn't require a concentration which could change the system being studied. So now I'm going to go over some sample considerations. So we're going to be talking about the physical sample. So what factors affect a CD spectrum? The sample concentration and cell path lengths are large, or a big deal, I suppose. Since CD is an absorption technique, which is based on Beer's law, where A is the absorbance, epsilon is the molar absorptivity constant, L is the cell path length, and C is the chromophore concentration. So therefore, the amount of light that's absorbed by the sample is going to be dependent on the concentration and path length, and is therefore critical to obtaining accurate CD data. The type of buffer and buffer concentration are also going to affect the CD spectrum, as well as the solution conditions such as pH, ionic strength, and temperature. Before we start discussing these factors, I first need to explain the second most important piece of data you need to acquire along with the CD signal, and that is the HT voltage, or the high tension voltage. The HT voltage is applied to the detector and used to amplify the signal and therefore the sensitivity. Since different wavelengths have different light energies, the HT voltage accommodates for fluctuations in the light level. It adjusts the amplitude of the signal depending on the DC voltage, which monitors the total signal output or total absorbance. So when a sample has an optimal concentration, shown by the figure on the left, A sufficient amount of light is transmitted through the sample and reaches the detector, and the HT voltage is low since the signal doesn't need to be amplified. However, if a sample absorbs too much light, shown on the right, not enough photons are going to reach the detector and the signal needs to be amplified, therefore increasing the HT voltage. If the HT voltage is equal to or above 700 volts, there are not enough photons being sampled by the photomultiplier tube detector to measure a reliable or valid CD signal, and we can't use these data points. The more photons reaching the detector, the better the signal to noise. So at higher HT voltages, while the HT may be below 700 volts, the CD signal is going to start to look noisier. Additionally, the further into the far UV you go, the less light that is available, so the HT voltage is going to increase at shorter wavelengths. While many samples do not require much sample preparation, there are a few things you want to keep in mind. So sample purity should be roughly 95% and can be checked via protein separation methods if it's not purchased from a vendor. The protein should be free of any additional chromophores or contaminants. So to check that there's little to no nucleic acid present in a protein sample, the absorbance can be monitored at 280 and 260 nanometers and the ratio of the two wavelengths calculated. So the protein is going to have a ratio about 1.7, while nucleic acids are about 0.6. So the lower that ratio, the more potential for nucleic acid contaminants in a protein sample. Dialysis can be used to remove any protective agents or buffer ion contaminants. Imidazoles and chloride ions pose issues to good CD data since both have strong absorbance in the far UV, which reduces the signal to noise of the protein spectrum. Imidazole concentrations should be kept under 1 millimolar if they have to be used, and chloride concentration below 100 millimolar, although the lower the concentration for both, the better. The protein solution should also be clear or transparent to avoid artifacts in the CD spectrum and can be done either through ultracentrifugation or filtration. So the figure on the right shows a protein sample that actually aggregated, and you can see white particulates that have actually crashed out of solution, as well as the fact that the solution itself is cloudy, and that's what we want to avoid, because a translucent sample could lead to differential light scattering or absorbance flattening. So differential light scattering occurs when particulates in the solution are too large relative to the incident light that's scattered. So the detector has an acceptance angle that describes the maximum angle of incident light that reaches the detector surface. While some light can be scattered and still fall within that acceptance angle and reach the PMT, any light that falls outside of that range does not reach the detector. So the detector can't differentiate between absorbed and scattered light. So it assumes that any light that is not detected was absorbed. So any light that doesn't fall within that acceptance angle, it just assumes is absorbed. So therefore, you get this apparent absorption, or the absorbed plus the scattered light, which increases, decreasing the CD signal. So because chiral samples have different refractive indices for left and right-handed circularly polarized light, the amount of scattering for the left and right-handed light components can differ, which is going to change the magnitude of the CD peaks and distort the spectrum. So the distortion of the spectrum and the extent of the scattering is dependent on the size and shape of the particles and the refractive indices of the sample and the solvent. So to avoid differential light scatter, the particulate size should be less than 1/10 of the wavelength of the incident light. So for hydrogel samples, solid samples, biomolecule samples that have a lot of salt concentration, this is why sometimes FTIR is used as a better secondary structure analysis technique, because the incident wavelengths in FTIR are significantly higher or longer wavelengths than they are for CD. So absorption flattening. In an isotropic sample shown on the bottom left, the proteins and therefore the concentration are uniformly distributed throughout the solution, while in an aggregated sample or a membrane sample shown on the bottom right, the protein chromophores are tightly packed together in localized areas, while the rest of the solution has little to no protein concentration. So this non-uniform distribution of chromophores leads to a breakdown of the Beer-Lambert law. and the effective concentration of the chromophores decreases, decreasing or flattening the absorbance and therefore the CD signal. So since absorption is dependent on the extinction coefficient of the sample at a given wavelength due to Beer's law, a correction term can't be applied to the spectrum since the absorption flattening is not going to be uniform across the wavelength range. So the overall spectral amplitude of the peaks is reduced as well as the magnitude, distorting the spectrum. So concentration and path length considerations. The optimal signal to noise is obtained when the optical density of the absorption max is 1. So conveniently, the sample concentration and cell path length can be adjusted to account for absorbance limitations because CD exploits Beer's law. So for example, if the sample absorbance is too large, but the concentration can't be reduced for experimental purposes, the cell path length can be shortened to acquire necessary measurements. So likewise, if only one cell path length is available, the sample concentration can be increased to obtain data with a sufficient signal to noise. This table shows some concentration and cell path length guidelines for a variety of chromophores, and I have highlighted the biomolecule chromophores here in green for your reference. Aside from the path length selection, the cuvette or the cell material and volume are also important parameters to consider when performing circular dichroism experiments. So quartz cuvettes are necessary for CD measurements due to their transparency in the far UV and because they typically have little to no birefringence, which can lead to artifacts in the spectrum. So the standard cuvette has either a 1 millimeter or a 10 millimeter path length, depending on the application, and can either be rectangular or cylindrical. Demountable cells are used when shorter path lengths are beneficial for reducing the overall absorbance if the sample or solvent concentration has too much absorbance. So demountable cells hold smaller volumes than the traditional 1 and 10 millimeter path length cuvettes, but you can't use these cells for temperature-dependent studies because they're not completely sealed, which can result in heat loss. So the demountable cell also require a demountable cell holder because those two cells are two individual plates which are sandwiched together and then secured in place with the demountable cell holder. It's also important to verify the path length of the demountable cells after the sample's been loaded to ensure that the correct path length, especially if you're going to calculate molar ellipticity or mean residue molar ellipticity or anything where there's a concentration and path length correction. Rectangular micro and submicro cells are also available for small volume measurements, and they come in a variety of volumes and path lengths. These cells have smaller apertures, so it's also important to purchase a black mass cell like the one shown here, and if the cell window is smaller than the instrument beam. JASCO also offers 2 microsampling accessories. So there's a microsampling disc for spectral scans, which uses only 2 or 10 microliters, depending on the path length. And then we have a capillary cell for thermal stability studies that holds about 10 microliters of sample and has a 0.5 millimeter path length. So while most quartz rectangular cuvettes have little to no birefringence and flat baselines, baseline measurements should be performed to ensure no optical artifacts are observed due to the strain on the cuvettes. So additionally, these cell baseline measurements can elucidate the cleanliness of the cell. So you can look at the cell baseline by just putting the cell either empty or with some water into the sample compartment and taking a measurement using the wavelength range you're going to use to obtain the sample measurement. So cuvettes can be cleaned by washing with water and or solvent, as well as detergents such as Helminex. For applications where the sample is really stuck to the sides of the cell, you can sonicate in Helminex. So you would put the cell in a solution of Helminex and sonicate it. You could let it soak in the Helminex detergent, or if that's still not doing the trick, it's also possible to rinse with concentrated nitric acid. So the buffer or solvent in the sample is also going to affect the CD spectrum. Solvents used for absorption measurements will typically suffice. However, the following conditions should be taken into consideration when choosing a solvent for CD measurements. So the solubility of the sample in the solvent, the transparency of the solvent in the wavelength range being probed, whether it is optically active, and the sample stability. So low absorbance or transparency is especially important for secondary structure studies in the far UV, since many solvents absorb strongly below 200 nanometers. The table on the right shows various buffers and their absorbances in a 1 millimeter path length cell with a 1 millimolar concentration. The addition of salts to buffers will also increase the absorbance and potentially induce scattering, which reduces the signal to noise of the spectrum. So sugar-based formulation buffers not only absorb highly in the far UV, but they also have a CD signal because they're optically active and should be avoided for CD measurements. So one of the most common questions I get is, can I use blank as my buffer? And I can 100% provide a variety of guidelines. However, the best way to check if your buffer system can be used for CD is just to run a measurement of the buffer in the wavelength range you want to obtain your sample measurement. So since we want the buffer to contribute very little to the overall absorbance, the solvent HT voltage should ideally be less than 450 volts. So any larger and the addition of the sample to the solvent will likely surpass that 700 volt threshold that we want to stay below. So the figure on the right illustrates different solvents and their wavelength limitations. So if I wanted to go below 200 nanometers, my only option really is to use this 50 millimolar phosphoric acid buffer. But say the only buffer system I could use was a citric acid buffer, but I really wanted to go potentially down to 200 nanometers, you could look at reducing the concentration of that citric acid buffer to get further into the far UV. So protein stability is really going to take precedent over the CD spectrum, because if your protein isn't stable in the buffer system, it doesn't really matter what the CD spectrum you get or how far you can get with the CD spectrum, because it's not going to accurately represent the state of your sample. So if the solvent absorbance is large and you can't reduce the concentration or limit the salt content or change the buffer system, what you can do is look at decreasing the path length, because again, we're looking at CD is based on a Beer's law technique, so you can look at concentration and path length. So this table shows solvents and their wavelength limitations using different Cuvette path lengths. So now I'm going to go into measurement parameter optimization. So these are the parameters of the actual instrument. So if you tuned in for our first CD webinar, I went over the importance of nitrogen purging for most CD measurements. So to quickly summarize, we want to purge the instrument monochromator of oxygen with nitrogen for two reasons. The lamp creates UV radiation, and when UV radiation interacts with oxygen, it creates ozone. Ozone is going to oxidize the mirrors in the instrument, which cause them to lose reflectivity, which causes less light throughput through the monochromator, which is going to reduce the signal to noise of the spectrum. Purging with nitrogen also avoids the absorption of oxygen in the far UV as well. So once you're in front of your instrument, you're going to turn the instrument on to warm up the lamp, and you're going to turn the nitrogen on to purge the monochromator. So the further into the far UV you need to acquire data, the higher the required flow rate. So if you are going above 185, you can start with 2 liters per minute. If you're going below 180, then you would need to crank up the flow rate to 5 liters per minute. If you open the software at this time, you're going to get this nitrogen gas replacement prompt, which is just a timer that reminds you to purge your instrument with nitrogen and then counts down for a designated amount of time. The default is 5 minutes, but you can change that to say 30 minutes in the admin tools. So here I have shown the parameter dialog box for the spectrum measurement program. This is a basic measurement program which allows you to acquire CD data as a function of wavelength. And this general tab displays the measurement parameter settings used to optimize the CD spectrum. So you have photometric mode, data pitch, scanning mode, scanning speed, DIT, CD scale, bandwidth, and accumulations. First, we'll start with the photometric mode. So the photometric mode is basically the signal being monitored, and you can select up to 4 channels, and the data is going to be acquired simultaneously. So if you want CD and absorbance, they're measured at the same time. They're not 2 subsequent measurements. I'm not going to go through all of these photometric modes listed on the left for the sake of time, but I do want to highlight that this is where you can select the 3 most common used modes: CD, HT, and absorbance. The start and end fields determine the wavelength range for the measurement. So for secondary structure studies, measurements are obtained between roughly 175 to 250. Tertiary structure information is acquired between 250 and 350, and DNA secondary structure studies are performed between 200 and 300 nanometers. The data pitch determines the number of data points collected at the specified interval and should be set so that 3 points are acquired for every nanometer that the bandwidth is set to. So for example, if the bandwidth is set to 1 nanometer, the data pitch needs to be at least 0.3 nanometers. So the last seminar, I discussed the instrument design and how the slit widths adjust based on the bandwidth dispersion. On the wavelength dispersion. The slit width defines the spectral bandwidth. So the wavelength dispersion created by the prism means that while the monochromator is set to a specific wavelength, there's going to be a Gaussian distribution of wavelengths exiting from the slits. The spectral bandwidth is the full width of this distribution at half the peak maximum, or the full width half max. The smaller the bandwidth, the smaller the slit dimensions, allowing less light to reach the detector and therefore decreasing the signal to noise. To keep the noise as low as possible without losing band shape and height, the spectral bandwidth should typically be selected as 1/10 of the natural bandwidth. So for example, the CD spectrum of ACS on the left shows well-separated bands with a natural bandwidth of over 20 nanometers, so a spectral bandwidth of 2 nanometers is more than suitable. However, in the lysozyme spectrum shown on the right, the peaks are significantly closer to one another, so selecting the appropriate bandwidth is more critical. By taking the first derivative spectrum of lysozyme, we can better determine the exact zero crossing and select a more suitable bandwidth. So the standard spectral bandwidth for CD measurements is 1 nanometer, but for high sensitivity measurements, the bandwidth can be adjusted to 2 nanometers to improve the signal to noise of the spectrum, because now you're getting more light throughput. JASCO offers 3 different scanning modes. The continuous scan acquires a CD signal at each wavelength while moving across the desired wavelength range. With continuous scan, the measurement time does not depend on the data pitch for the step resolution and can be done at higher speeds, so this is the mode that can be used to obtain data with a better signal to noise and a shorter acquisition time. The step scan mode stops the monochromator at each wavelength based on the data pitch, so the measurement is much longer than the continuous scan mode. And the auto step scan mode performs a step scan while automatically adjusting the digital integration time to obtain a constant signal to noise ratio by specifying upper and lower DIT limits. The figure on the right shows a continuous and step scan overlaid in red and blue respectively, and the difference between the 2 spectra is shown in pink. So you can see that there's virtually no difference between the 2 scans if the correct measurement parameters are selected. So going forward, now I'm going to explain to you how to choose those correct parameters, but going forward, I'm going to assume that we have selected the continuous scan mode. So the DIT and the scanning speed are extremely important to optimize when trying to achieve accurate data and good signal to noise. The DIT is the digital integration time, or the response as it's called in older software, and it's the time in which the data is integrated over. So basically, the detector sees incoming photons and passes them along for signal processing. The DIT specifies how long the detector sees these packets of incoming photons before it sends that information to be digitized. The square root of the digital integration time is proportional to the signal to noise and is likely going to contribute the greatest to increasing it. The scanning speed specifies how quickly the monochromator moves to obtain data points. So the scanning speed has to be taken into account when setting the digital integration time and vice versa. So when selecting these 2 parameters, the digital integration time multiplied by the scanning speed must be less than 1/10 of the full width half max of the peak of interest so that you do not average over any data. So for example, if the DIT is 1 second and the scanning speed is 10 nanometers per minute, if we convert the scanning speed to nanometers per second and multiply by the DIT, we get 1.67 nanometers. This is our response wavelength width, or the width that the signal intensity is averaged over. So in this example, if we're looking at the photometric value at 210 nanometers, it's going to be the average of the signal between 208.3 and 211.7 nanometers, because I added and subtracted 1.67 nanometers to the 210 nanometer wavelength we're looking at. So how do you determine what digital integration time and scanning speed to use so that you don't average over any data? The DIT and the scanning speed should be set so that the response wavelength width is 1/3 or less of the full width at half max of the target peak. So in this spectrum here, our target peak is at 269 nanometers, and the full width half max is 28.1 nanometers. So 1/3 of that is 9.4. So our wavelength response width has to be less than 9.4 nanometers. So the tables here provide a list of response wavelength widths calculated from various digital integration times and scanning speed pairs. So these tables are more for future reference, but I've highlighted the optimal pairs here in green. And from our previous example, where the maximum response wavelength width we could use was 9.4, based on these tables, we can use any of the pairs shown here. But with so many options still, how do we know which one to choose? So that's partially going to depend on what takes precedent in your measurement. Is it acquisition time, or is it the signal to noise? So obviously you want the best of both worlds. You want a short measurement time and great signal to noise. And while for some lucky samples that happens, others you have to choose which is more important to you. So to prioritize the signal to noise over the acquisition time, it means you're going to have to increase the digital integration time, which means you potentially have to lower the scan speed to meet that required wavelength response width of your sample. Increasing the DIT doesn't really add any time to the measurement, maybe a few seconds, but if you decrease the scan speed from 100 nanometers per minute to 50 nanometers per minute, you actually double the measurement time. If you want to prioritize measurement time over signal to noise ratio, increasing the scan speed or potentially having to decrease the DIT. So for samples that already have a decent signal, like say alpha helical versus a beta sheet protein, the DIT has a smaller effect on the signal to noise. So while the scan speed itself doesn't have a significant effect on the signal to noise of most spectra, here's an example of how the DIT does. So on the left is an alpha helical protein, and the spectra on the right is a beta sheet protein, and I've increased the DIT for both of these. So the alpha helical protein shows that if you increase the DIT, there isn't a huge difference in the signal to noise of the spectra because it has such a large signal. The only huge difference is going to be at the shorter wavelengths, so below 190, where we already know there's less light throughput at these wavelengths. However, if we look at the beta sheet protein spectra, you can see that as the DIT is increased from 1 second to 4 seconds, there's a significant increase in the signal to noise of the spectra. And that's partially because the signal is already extremely low for this beta sheet protein. So once we have optimized the scanning speed and the DIT, if the signal to noise is still relatively low, we can look at increasing the number of spectrum accumulations. So these are the number of spectral scans that are automatically obtained and averaged together. So the spectrum signal to noise is proportional to the square root of the DIT multiplied by the number of accumulations. While increasing the number of accumulations will increase the signal to noise, it also increases the measurement acquisition time, since the measurement is repeated for the number of accumulations that you specify. So if you specify 5 accumulations, it's going to take 5 consecutive measurements. Selecting accumulations also means each individual measurement will not be saved. It only will save the average accumulated scans. So the spectra on the right show a single scan in blue and 3 accumulated scans in green, and the data has been offset to see the differences in these two spectra. But you can see that the accumulated scan in green has a better signal to noise than that single scan shown in blue. Additionally, if you want to acquire, say, 5 scans and have each spectra for each scan saved individually, and then potentially average them together manually yourself at a different point in time, if you deselect the accumulations box, it's going to pop up cycles. So cycle is just going to be how many measurements do I want. So for instance, this is really handy because if you don't know how many accumulations you need to increase the signal to noise of your spectrum, if you can only do 3 accumulations instead of 5 accumulations, that's going to save you almost half the amount of time. So if you initially were to do 5 cycles, you get each individual scan, and then you can average, say, 3 of those scans together to see if that 3 accumulated scans is a sufficient signal to noise than, say, 5, which is going to add on the acquisition time. So last but not least, we have the CD scale. So the CD scale specifies the range of the detector, while the fluorescence scale specifies the range of the detector in the fluorescence mode. It is important that this is properly set because if the CD signal exceeds the upper limit of the range specified by the CD scale, the data can be distorted. So the scale needs to be set above what the actual sample signal is displaying to account for any instrument noise. So if you have a 50 millidegree CD signal, you have to set that more than 50 degrees. So I would say a good starting point is 200 millidegrees. However, if the sample has a very small signal, like less than 5 millidegrees, you can start with 200. So how do you know if the range has been exceeded? So there are 2 ways of doing this. You can do so during the measurement and after the measurement. So during the measurement, you have this status tab on the left-hand side of the measurement window, and it will say CD signal overload. If that button is red, it means that you have exceeded the CD scale specified. If it's green, it means that the spectrum is still within that CD scale range. If you have already obtained a measurement and you want to make sure that you didn't potentially distort the data, in spectra analysis, if you select the spectrum of interest and click the information icon, if you scroll down, it's going to say CD overload detect if the CD scale has been exceeded. If it hasn't been exceeded and it's still within that range, that line item just won't be there. So to summarize, to increase the CD signal, you can increase the protein or sample concentration or increase the path length. To decrease the HT voltage or absorption, you can decrease the buffer concentration and potentially remove any faults or imidazole, decrease the sample concentration, decrease the cell path length, or open the bandwidth. To increase the signal to noise of the spectrum, you can increase the DIT, which possibly means you have to decrease the scanning speed, increase the number of accumulations, or open the bandwidth. And to shorten the measurement time, you can increase the scanning speed, which means you possibly have to decrease the digital integration time, or reduce the number of accumulations if there are more than 1. So a quick side note on just 2 comments about some troubleshooting and a quick tip. This little beauty here on the right is a spacer for the 1 millimeter path length cell. And this is used to keep the cell vertical in a temperature cell holder, which most users keep as standard in their instrument because the temperature cell holder is made to hold a 10 by 10 rectangular cell. So the hole in the middle of this spacer is the dimension of the light beam. So a 1 millimeter path length cell holds between 250 and 450 microliters of sample. If you don't want to fill the cell all the way to conserve some sample, you can hold the spacer up to your cell and then fill the cell with the sample just so that it completely covers that hole. You also want to take care that the meniscus is not in that hole or the beam path as well. So in regards to the HT voltage, if your HT voltage is above 100 volts, there's something blocking the detector. So the spacer could potentially be upside down. That hole in the spacer needs to be towards the bottom. If that is in the correct position, then you want to check that there's no tubing or wiring that's blocking that light path. If the HT voltage is at 0, there could be 2 problems. So first, the shutter could be closed. So this is the shutter icon. When you don't, it's basically a door. So when it's just brown, that means that the shutter is closed. If you click on it, it should open and it looks like a door is opening and there's like a little yellow light coming through. That means that your shutter is now open. If you have clicked that icon and there's that yellow light coming through and you still have a voltage of 0 for the HT voltage, The other option could be that the sample lid is open or ajar. So you just want to make sure that is completely closed as well. So some data processing functions. Before I go into this, I want to quickly mention baseline and background measurements. So baseline and background, they're interchangeable in this term. It's just you're measuring the solvent. So you have two choices when you're doing a baseline measurement. You can measure the solvent as a baseline, in which case it's going to be automatically subtracted from your sample measurement, or you can measure the solvent as a sample and manually subtract the solvent spectrum from the sample spectrum at a later point. So if the automatic baseline subtraction is selected, which can be done here, so in the control tab in correction, you would hit the baseline. This B icon is going to be highlighted. So you would put the solvent in the sample compartment, select the B icon. It would take the baseline measurement. You would then put the sample in the sample compartment, select the S icon for sample measurement, and then your sample spectrum is automatically going to be subtracted. That baseline, solvent baseline, is going to be automatically subtracted from the sample spectrum. You need to keep in mind that if you do a baseline correction, you don't get the raw sample spectrum. So it's always going to be corrected by the baseline that you previously took. If you're okay with manually doing a subtraction after you acquire your measurements, you would hit none for your correction. That B icon would be grayed out, and then you would put your solvent in the sample compartment and click the S icon to do the solvent measurement, and put your sample in the sample compartment, hit the S icon to do a sample measurement, and then manually subtract them. So how do you do a manual subtraction? So in spectra analysis, you're going to open the sample and solvent spectra and overlay them in the same view. And then you're going to go to processing subtraction. This window then pops up. On the top left-hand corner is the order of operations. So in green, I have my sample spectrum, and in blue, I have my buffer spectrum. The top plot in green shows the raw sample spectrum, and in blue shows the raw buffer spectrum. And then the bottom plot shows the corrected sample spectrum. So now it's sample minus buffer. You would then hit OK, and it creates a new memory where you can now save the corrected sample spectrum separate from the raw. So CD spectra are reported as ellipticity and measured in units of millidegree, but can easily be converted based on the user's application. So delta epsilon, or the molar absorbance, normalizes the circular Dicroísm spectra based on concentration and path length. Molar ellipticity also accounts for path length and sample concentration. And then when analyzing the secondary structure components, the number of amino acid residues in the protein must be accounted for, and the ellipticity is converted to mean residue molar ellipticity. So to calculate the mean residue molar ellipticity, we can use the optical constant processing function in spectra analysis. So you would open the spectrum of interest in spectra analysis, go to processing, go to CD options, and then select optical constant. This dialog box pops up. You select your concentration unit, whether you want to specify it in weight per volume or molar concentration. Your y-axis is molecular ellipticity. And then you have to enter the path length or the concentration in these path length and concentration text boxes. So if you're only going to do molar ellipticity, you can just enter the molar concentration yourself in that concentration box. However, if you want to account for the residues in the protein to calculate mean residue molar ellipticity, and you don't want to calculate it yourself, you need to hit this calculate concentration box, and you get this dialog where you input the concentration of the protein in moles per liter, and then you enter the number of amino acid residues and select OK. And then it goes back to that optical constant menu, and it auto-populates the concentration per residue. You then manually enter the path length, select OK, and then you get a new spectrum in units of molar ellipticity. So a quick comment, whether you calculate molar ellipticity or mean residue molar ellipticity, the y-axis unit is still just going to say molar ellipticity. And then I want to mention this file converter program because not many people are aware of it, but it's pretty handy. So the file converter program is used to convert JWS files, which are the JASCO Spectrum Manager spectrum files, to text or JCamp, or if you have older software and you want to convert to a newer software, or vice versa. So this program batch converts entire folders of files, since you can already convert or export individual scans in spectra analysis. So you have a source that you need to specify the format. So say we're going from a version 1.5, so Spectrum Manager 1.5 to a text file. You then specify the destination, so text, JCamp, JWS version 2, JWS version 1.5. Your source folder, you specify a destination folder, which has to be separate or different from the source folder, and then you would select convert, and those files would automatically be converted and put in the folder that you specified. So with that, I just want to quickly remind you of some JASCO educational resources. Our next webinar will be on FTIR theory, instrumentation, and techniques, and given by Dr. James Burgess on Tuesday, May 5th at 2 p.m. We have some more webinars coming up, FTIR microscopy, Raman microscopy and imaging, and SFC theory and applications. You could also view our past webinars on our website as well. So the PowerPoint or the PDF is there for you to upload as well as to re-watch the webinar. We have some ebooks and some tips and tricks posters on Raman, fluorescence, FTIR, and CDs. And then we also have our knowledge base, which is a database for literature articles that's been peer-reviewed using JASCO instruments. So if you want to know if your application has been performed using one of our instruments, you could enter your keyword and search there, or if you are looking for some experimental advice using a peer-reviewed paper, you can also use the knowledge base to do that. So thank you for attending our webinar or CD webinar part 2. And if you have any questions, I'd be happy to answer them.
Okay, thank you, Leah, for that very nice presentation. As Leah mentioned, these video and the slides are going to be available soon. And with that, we want to start our questions session.
So do I have an example of what a distorted spectrum would look like? Would it simply look clipped if the range is wrong? So that's a really good question. So I'm not sure if you guys are familiar with fluorescence spectra, but typically if you exceed the detector or swamp the detector for a fluorometer, it flatlines the peak. With CD, you don't get a flat line of the peak, you actually get some shifts in the spectra. So it's not very obvious that you've exceeded that measurement range because it's not going to flatline anything. It's just going to potentially distort the shape of a peak or shift the peak. Can I measure the secondary and tertiary structure at the same time? That's also a really good question. So secondary and tertiary structure studies have different concentration and path length requirements. So it's not ideal for you to, so if you're going from say 180 to 350 to do secondary and tertiary, it's a little tricky. You could potentially try to optimize to do that, but typically no, because you typically need a larger path length for tertiary structure than you do for secondary, because the transition is a lot weaker in the tertiary structure, the near UV, than it is for the far UV. If I'm trying to determine the DIT and scanning speed, does the instrument software tell me if I use incompatible settings? So yeah, so I mentioned that the DIT multiplied by the scanning speed has to be less than 1/10 of the full width half max. So if you set that value incorrectly, there's actually, I want to say it's a 200 value where it will actually pop up an error bar and say reset or respecify your DIT or respecify your scanning speed, and that's just basically telling you that you set them too large, so you just need to either decrease the DIT or decrease the scanning speed. What should the HT voltage be with nothing in the sample compartment? So typically, if you're getting a brand new instrument, the HT voltage with nothing in the sample compartment should not be 0. It's typically going to be about 250 volts. If you put a Peltier cell holder in there, depending on how long, if you say you've had your instrument for like 5 years, and you've had the Peltier cell holder in it the whole time, if you've been doing a lot of temperature experiments, those windows can get dirty. So sometimes, if they are, that could potentially reduce the light throughput. So your HT voltage is going to be a little bit higher. But for a brand new instrument, it's about 250 volts. That actually brings me to an excellent point that I wanted to make. So I suggest this to people whenever I go in for training. Keep a logbook of, who's using the instrument, when they're using the instrument, but also one of the things you want to monitor, or each user should be monitoring when they come up to use the instrument every day, is what is the HT voltage? So at 300 nanometers, you move your wavelengths to 300 nanometers, and with no cell sample, you can leave the Peltier cell holder in there, but with no cell or sample in the sample compartment, what is the HT voltage? And at 300 nanometers, your HT voltage should be below 300 volts. I said that it's a 250 volt starting typically, so over the course of the instrument and as your lamp decreases light throughput because of age, that value is going to get a little bit higher because the signal has to be amplified a little bit more. But you really, and you might actually notice this in your spectra, that your signal to noise is decreasing with the life of the instrument or the lamp. So you definitely want to monitor and make sure that voltage is below 300. And if it's above 300, it starts to creep up there where you do notice significant differences in your spectra. Then you can either change the lamp if the lamp hours are exceeding 1,000, or you can look into getting new mirrors, so M0 and M1, which are right by the lamp, and get the brunt of that oxidation. Is it okay to adjust the parameters to have a good signal and scans for samples that I would like to compare? So for example, comparing samples at different pH. So yeah, you might have to, you might have some, there's definitely some samples which will aggregate if you have a very low pH. So I would definitely recommend adjusting your parameters based on each sample. You can still compare your pH at 11 and pH at 3 of your sample. You're just optimizing the signal to noise here, but you're still getting the same signal. It's just whether or not there's more noise in there or not. So you can still compare them. I'm not sure how to word that differently. Is there an appropriate way to use demountable cuvettes? Yeah, that's it. So I typically use volume through leaking. So the best answer I have for that is each demountable cuvette has a specified volume that the slides or the cell holds. I would really try to stick to that. Like, don't just kind of fill it up till what you think is full. It's kind of hard to explain this without showing you, but I will do my best. So typically when I fill a demountable, I have one slide on the bench, and I have another, the top slide on top of the very bottom half of that bottom slide. And as I fill, I kind of slide the top half up the cell. So this kind of pushes all the air bubbles to the top of the cell. And then right before I seal it, I put the very last bit of volume in. That typically helps with not having any volume leaking out. And that typically, so that action in itself typically seals the demountable cells pretty well. The demountable cell holder isn't really there to seal the cell per se, it's just to keep it securely in place. if you kind of do that sliding up the top slide to the bottom, that typically will seal it, because and if you use the correct volume, you won't get any volume leakage. But that's typically how I do it. I will say that there is so the demountable cells are typically, you get like a 0.01, 0.05, 0.1, 0.5, 0.2. The smallest non-demountable sealed path length is a 0.5, which kind of comes in handy sometimes. So that's another option too. What bandwidth for the 300 nanometer for HD voltage? I think it's 1 nanometer. Can I take a video doing the demountable cuvette? I can definitely do that. I will have to remind myself to do it tomorrow. But yeah, I can do that and post a video somewhere. How to validate CD protein secondary structure measurements, since it shows a lot of variation in terms of ratio at different points in time. So I'm not sure if I'm answering this correct or answering your exact question, but in regards to how I would validate to make sure my CD secondary structures were accurate, in regards to different points of time, I'm not sure if you mean the samples changing at different points in time, but how to validate that, what I think would be a great idea is to build a reference set. So if you have 10 of your folded protein samples, take 10 different spectra of them and then do the secondary structure analysis, and then get a range of what the secondary structure percentages are for those 10 samples. So whether you want to make 10 completely different samples or just take the sample in and out of the sample compartment and do a different measurement each time, however you want to kind of create variation in that reference set, that's up to you. But then once you get a range of what the secondary structure should be of that reference, then you can kind of, once you do the analysis for the other protein, you can kind of then determine if the variation in these non-reference protein samples is just variation in the secondary structure estimations you're doing, or if it's actually variation in the spectra, which is kind of like the idea behind the Spectrum QC test program. Why not encase monochromator and vacuum device to reduce the requirement for nitrogen flow? So we don't have different compartments for our instrument, just so we don't have to put the light through another. We don't want to not attenuate the beam, but we want to really keep the optimal light throughput. So by putting any material in between the light and the sample, you're slightly reducing that light throughput. Is there a calibration standard available? Yes, so the CD scale is calibrated using ACS, which I showed in that bandwidth section. To calibrate the CD scale with ACS, you want 60 milligrams in 100 milliliters of water. You're going to put it in you can do it in a 10 millimeter path length cell. Typically, you're looking at 290.5. There is also a peak at 194 nanometers, I believe, which you can look at the CD scale in the far UV. If you are looking at the CD scale for ACS in the far UV, you have to go down to a 1 millimeter path length cell. But at 290.5 in a 10 millimeter path length cell, your signal should be 190 plus or minus 1%. And then if you do go to the 1 millimeter path length cell to go in the far UV, it's going to be 19 plus or minus 1%. And then the far UV peak at 194 should be twice as large negative amplitude is the positive peak at 290.5. If you guys don't have any more questions now, you're also very welcome to email me at a later point in time if something comes up with your spectra as well. How about the 0.5 millimeter cell for far UV? You can definitely use a 0.5 millimeter cell for far UV. Just keep in mind that you might need to slightly increase your sample concentration, depending on what your signal is already, to get a better signal to noise. If you're trying to use the 0.5 millimeter cell for far UV to cut down on sample absorbance, then you can definitely look at that too. Or not sample absorbance, I'm sorry, buffer absorbance. I typically go with a 0.5 millimeter cell, specifically if I'm doing temperature measurements because it's sealed, and with the demountables, you can't go to a short path length cell like those and do temperature studies because they're not sealed. Are there any extra things to note when working with a buffer containing detergents, say membrane proteins? So detergents are a little tricky because those do have a good bit of absorbance below, or in the far UV, so below 200 nanometers. The best detergent to use with CV. I can't think of one off the top of my head. The Triton keeps coming to mind, but I know that has far absorbance. So that kind of depends, because it depends what your concentration of the detergent you have to use is. If you can get a pretty low concentration, then there might be more, you might have more detergent options that you could potentially use than if you have to have, say, 100 millimolar concentration of detergent. The other thing I will mention, just because you brought up membrane proteins, you have to be a little tricky with membrane proteins. And when I think of membrane proteins, I'm assuming that you're potentially working with the membrane in the sample. So this, you might also have some scattering from the membrane as well. So just be a little bit careful when you're obtaining these measurements. Actually, an interesting point to that would be, okay, if I have a sample that I know is going to potentially scatter, I have no choice. I have to use the sample. I don't have an FTIR to use. CD is so much easier to use than FTIR in regards to secondary structure and protein samples. But what you could potentially do is if you place your sample in the standard cell holder. So basically, everyone should get, the instrument comes with a standard cell holder, and you get a little boat that comes with it. So there's a rail on the standard cell holder that this boat goes in. You can actually move that boat, and therefore the cell that the cell is held in this boat, you can move that closer to the detector. So the detector is on the right side of the instrument. You can move that as close as possible to the detector. So any potential light that's scattered is going to, if you shorten that distance of the cell from the detector, there's a better chance that that scatter is actually going to be incident on the detector surface. And you could potentially reduce any artifacts from that light being scattered and that apparent absorption that I discussed earlier. And that person that asked about the detergent, if you shoot me an email, I can look it up and give you a better answer. And then understanding how to measure the demountable cuvette passings would be nice. That actually, the best way to do that is getting an interference pattern, which is typically obtained with FTIR. So that is a little trickier said than, or done than said. Easier said than done. But that's typically how you would do it. I guess if there are no more questions, then thank you all for attending our second seminar. And please join us again next Tuesday at 2 p.m.